welcome again to this new lecture of solar photovoltaics, so principles, technologies and materials course. So we have been talking about amorphous silicon solar cells, and just in the end of last lecture we had one or two more things to say. So we will just do that in recap of previous lecture. Okay. So if we do recap of previous lecture, we talked about amorphous silicon technology, which is essentially a pin junction technology. So we have a intrinsic silicon layer, which is the main absorber layer, then we have P silicon, and then we have N silicon, and on both sides we have contacts, and we can have glass substrate on this technology. Here the important thing is that silicon is hydrogenated. So, and this hydrogenation reduces the traps or tail states within the band diagrams. As a result, this improves the performance. So one thing is you use hydrogenation. Second thing is amorphous silicon is also useful to create a multi-junction solar cell, because if you mix it with amorphous germanium, then they make a solid solution. So you can tailor the band gap. So you can tune the band gap, and this allows you to make multi-junction technologies to harness light in a more effective way. Coming to efficiencies of these solar cells. So efficiencies of amorphous silicon are about 10% for amorphous silicon, and these are they give you a VOC of about 0.896 volts, and JSC of about 16.35 milliamps per centimeter square, and the fill factor in these devices is generally lower than, you can see that this is lower than crystalline silicon. Crystalline silicon you get very high current of the order of 40 milliamps per centimeter square. In this case you get a current of about 16.35, and fill factor is about 65 to 70%, which is lower than again lower than crystalline silicon, where so this is about 40 in case of crystalline silicon. In this case it is about 80 to 85. So very high fill factor is obtained in case of crystalline silicon solar cells. So this is the impact of structure and defects in the structure on the performance. However, nevertheless, it was a very potent technology upon a time, amorphous silicon, and very talked about technology. So now let us look at other kind of solar cells also. So now we will look at the next technology that we will consider is the cadmium telluride based solar cells. Cadmium telluride basically belongs to the family of chalcogenides, and chalcogenides are basically, you can say, are zinc sulfide, zinc selenide, zinc telluride, and then we have cadmium sulfide, cadmium selenide, and cadmium telluride. So these are 6 chalcogenides we have, and CDT belongs to this family. So typically the devices from the perspective of solar cell, although you can make multiple combination, the most successful combination has been CDS and CDTE. This is a very successful combination. CDS acts as a N-type material, and CDT acts as a P-type material, and CDT has a band gap of about 1.44 eV, and cadmium sulfide has a band gap of about 2.42 eV. So this is the most successful junction that this system has produced. So band gap of cadmium telluride, as I said, EG is approximately 1.45 to 1.50 eV. You will find in some cases 1.50, in some cases 1.45. It's very close to ideal band gap, and it's a direct band gap semiconductor. As a result, high optical absorption is there in this material. So, absorption coefficient is greater than 5 into 10 to the power 5 per centimeter inverse, which is very high as compared to materials like silicon. Silicon has quite low absorption coefficient as compared to this material. It has very good absorption between UV to about 825 nanometer. Excellent light absorption between in this range. So, let me also just give you a value of silicon. So, silicon has a value of about I would say absorption coefficient is so within so silicon has absorption coefficients of about, whereas in case of silicon, if you consider, it varies from 10 to the power 3 to 10 to the power 5, but it has for useful energy range, it has lower absorption coefficient in the useful range. Of course, it increases for the shorter wavelengths, but most of the part of solar spectra lies in the visible and IR. So, as a result, in that range the absorption is lower. So, lower in the useful lambda range. So, between 10 to the power minus. So, gallium arsenide has very good absorption coefficient within the useful range. So, you can say it is within the useful lambda range, that is from UV to IR. So, now let us look at and for electrons, for energies higher than Eg and of AM 1.5, let us say at AM 1.5 you have nearly 99% absorption in a thickness of about 2 micron. So, 2 micron thin film is sufficient to give you complete absorption of light, which is fantastic. So, cadmium telluride is, if you look at some of the material aspects of cadmium telluride, cadmium telluride is a if you want to make it N type, you have to use either cadmium excess or interstitial cadmium or indium as a dopant. These are methods to make N type, and which is less common. More common is P type. So, P type is tellurium excess or cadmium vacancies, and gold is used as a dopant. Okay. So, basically cadmium vacancy is when cadmium goes out, cadmium at cadmium site when it goes out. So, you have VCD plus CD, cadmium goes out, let us say. So, VCD is essentially negatively charged, and this gives you holes, negatively charged like this, and this gives you holes. So, this makes it P type. Okay. And similar defect reactions you can write to tellurium excess. So, when you put tellurium in there, so tellurium goes to interstitial site, and this is negatively charged tellurium, and this gives you holes as well. Whereas in this case, if you put cadmium, cadmium goes to interstitial site, it has a positive charge, as a result it will give you electrons. Okay. So, this is how you write the defect reactions in this material. Now, the typical device design in this material is so you start from glass substrate, let us say this is glass. So, I am going to put glass on top, okay, because I just want the I want the light to come from top. So, So this is light, okay. And so first is the glass, then we put a next layer of ITO, which is the indium tin oxide layer, which is a TCO, indium tin oxide, which is a low resistivity electrode. It's basically indium tin oxide, INSNO. So it's a solid solution of IN2O3 and SNO2, okay. So you can say it's basically 2 plus delta. So for every 2 minus delta, yeah. Or let me put it this way, you can write the, so it's basically solid SNO2, indium doped tin oxide. So indium is little less in quantity, so you can say this is X, this is 1 minus X. So as a result, you are going to have little bit lower in oxygen. It's going to be fine, but it's highly conducting. It's like metallic behavior. So a thin layer of indium tin oxide. Then we have a high resistivity tin oxide, a thin layer. So high resistivity tin oxide, which is used as a sort of to reduce the surface recombination. And then we have on top, at the bottom in this case, N doped CDS layer. So this is NCDO, NCDS, not O. This is called as a window layer, okay. And then we have here a slightly thicker layer of PCDTE, which is the main absorber layer, okay. And then we have what we call as a gold or nickel aluminum contact. So this is top contact, this is the bottom contact, okay. So this is P type contact, this is N type contact on top, and this device has a thickness of 3 to 5 micron on this side, and it has a thickness of 50 to 100 nanometer on. So main layer is about 3 to 5 microns, that is CDTE layer, and the window layer, that is for that is to form a junction, basically is of cadmium sulfide, which is the N type semiconductor, and this is from 50 to 100 nanometer. And in between there is a possibility to introduce you can also introduce a passivation layer. So at this point one can have a thin passivation layer. Can be inserted. Mostly these, so this is a super straight configuration because the light comes from substrate side, and these are the most common ones. You can also use substrate configurations, but these are most commonly used configurations for these solar cells. N type CDS has a band gap of, as we said, N CDS has a band gap of 2.4 EV, 42 EV, and P CDTE has a band gap of nearly 1.44 or 45 EV. And we get a differential of about, if you look at the differential, it's about 1.02 EV between the two. And they have pretty good, however this junction has slightly higher lattice mismatch. The lattice mismatch is about 9.7% between the two materials. So these materials give you very high efficiencies. Right now cadmium telluride based solar cells have efficiencies of the order of, so CDTE based efficiencies are of the order of nearly 21%, nearly 21%. It may have changed, and they give you a VOC of about 0.88 EV approximately, and JSC of about 30 milliamps per centimeter square. This is at the cell level, not at the module level. Okay, module level it's lower, and the fill factor is nearly 80%. And the company which is very gung-ho about this technology is First Solar. First Solar is one of the biggest manufacturer of cadmium telluride solar cells in the world, and this technology has a lot of potential. Now, from the materials perspective and the design of materials perspective, there are a few things which are done in this to achieve good efficiency. So, material improvements. Maybe first we can talk about the way you make it, and then we can come to the improvements. Okay, so we will first go to manufacturing. So, by the way, CDT, if I haven't told you, CDT has a structure which has a zinc blend structure. Okay, so it has zinc blend structure, which is ZNS based structure. So here sulfur makes the FCC lattice, and zinc occupies the tetrahedral sites, similar to diamond cubic, except that in diamond cubic both the atoms are similar. Here two atoms are different. So in this case, tellurium will make the FCC lattice and cadmium will go to the tetrahedral sites. So in some sense you can say tellurium acts as an ion and cadmium acts as a cation. And this material, before we go to manufacturing, just I wanted to also tell you that this material has large enough mu E and mu H. Mu E in this material is about 500 to 500 to 1000 centimeter square per volt second, and mu H is about 50 to 80 centimeter square per volt second. And it also goes a sublimation reaction, that is CDT can be sublimated to CD plus half TE2, and the melting point is about 1365. So TM is about 1365 Kelvin. So it's not very high temperature. So as a result, it can be processed little easily as compared to silicon and other materials which require higher temperatures. So from the manufacturing perspective, the phase diagram of this material is something like this. So if you plot percentage TE, so this is 0 to 100 percentage TE, and if I plot this is temperature in degree centigrade, the melting point is about like this. This is the phase diagram like. So tellurium has a melting point which is lower, of course, so I would come down here. So it's about 420 degrees centigrade or so tellurium, and cadmium has a melting point of about 700 degrees centigrade, about roughly, I don't know, maybe 680 or something, and this has a melting point of about 1092 degrees centigrade. So it has a nice simple phase diagram that allows you to achieve stoichiometry quite easily, and both these cadmium and tellurium vapors have higher vapor pressures. So when they have higher vapor pressure at relatively lower temperatures, it's easy to make using various processing techniques like evaporation and so on and so forth. So typical steps for deposition for this is, so if you look at the steps, so the first step is deposition of, so steps in manufacturing, deposition of CDS layer, and this is on TCO/glass. Okay, this is the first step, and this layer, as I said, is very thin. Okay, so if you look at the previous slides, this layer is about only 50 to 100 nanometer. So deposition of this layer, then we have deposition of CDTE deposition, then we have deposition of then we do a chemical treatment. So in the manufacturing there is a chemical treatment which is called as CDCl2 treatment, and this is a very important treatment as far as performance of the solar cell is concerned, and then we make a contact. Contact formation, which is either of nickel or graphite. You can also have gold, many materials. So generally CDT formation, if you look at CDT formation first, CDT formation can happen by reaction of CD and TE2 vapors and then deposition, okay, on a surface. This is typically something which happens in physical vapor deposition process like evaporation, so evaporation, sublimation, you can have sputtering also, thermal deposition, so all these processes. So you can have sputtering, you can have thermal evaporation, you can have sublimation, etc. All these physical vapor deposition in which you physically take the atoms of cadmium and tellurium together either in the atomic form, in the plasma form or in the vapor form, make them react at high temperature and then let them deposit on the substrate, on a heated substrate. So this is reaction of CDT to vapors slash atoms or in the plasma form and then deposition. Okay. So essentially you have a substrate and you have the CD and then you have T2 and they react together and they form a thin layer of, so these condense here and they form a layer of CD TE with the reaction CD plus half TE2 giving you CD TE. Okay. It is also possible to make this layer by galvanic reduction. So galvanic reduction of cadmium and tellurium ions at a surface, at a substrate. So this process will be called as electro deposition. So you must have a source of cadmium ions, you must have a source of tellurium ion, and then you make them diffuse towards the substrate which acts as an electrode, and then cadmium and tellurium ions they deposit on electrode giving rise to cadmium telluride formation. And then there are other chemical methods one can use. Where one uses the precursors. So use of precursors, or you can say salts of cadmium and tellurium. So these could be, and so these processes are such as MOCVD, or you can have spray deposition and so on and so forth. So here, as I said, the precursors come together, they react with each other, they form CDT which deposits on a substrate, and then excess of everything goes out of the system. Okay. So there are various processes that one uses. So as I said, CDT can be deposited by evaporation. So in evaporation, CDT, so you have a substrate. So if you look at evaporation, you have a source of solid TE, CDTE, this is CDTE source. You evaporate it 700 to 900 degrees centigrade. The vapors go out, these are vapors, and then you have a substrate here. These vapors deposit on this substrate and forming and this is at minus 10 power minus 6 torr vacuum, and substrate is held at about 400 degrees centigrade, and then you make a thin film formation. All right, this is how it happens, so this gives you thicknesses of the order of 1 to 5 microns at a deposition rate of about 0.01 to 0.05 micron per minute. Okay. Similar thing you can do with the sputtering. Instead of having a evaporation, you will have, so in sputtering you will have a source of cadmium, you will have a source of tellurium. This is the substrate. You apply electric field to both of them in the presence of a magnetron, and there is an argon gas, so they create a plasma. This plasma will contain Cd plus ion, tellurium ion, minus ions along with argon or some other gas ions. They will be pushed towards the substrate by applying a bias, or maybe it is at a ground, and these atoms, when they reach there, or they react Cd plus half Te2, giving rise to CDTE. So you physically eject cadmium ions and tellurium ions from this and make them react on the surface. Okay. So these argon ions will attack the substrates and pull them out. This is called as physical sputtering process. And then you can use closed space sublimation and vacuum thermal vapor transport deposition and so on and so forth. And all of these processes will operate at various deposition rates, and deposition rates for evaporation will be lower. Sputtering will give you deposition rate between about 0.1 micron per minute, and then sublimation etc. will give you sublimation will give you 1 to 5 micron per minute. So if I write sublimation, that will give you 1 to 5 micron per minute, and so that is how you will form CDTE. And then you can also do it by galvanic reduction. So galvanic reduction, basically what you will have is, you will have so this is galvanic process. In the galvanic process you have a box in which you have a electrode, and you have a electrolyte which consists of both the ions. This is kept at about 80 degrees centigrade, and you stir it. You have a counter electrode as well. This is minus, this is surface positive, and basically you have galvanic reactions that occur. So you have HTeO2 plus giving rise plus 3H plus 4E giving rise to Te plus 4H2O, and this has a reaction potential of 0.559 voltage. Then we have Cd2 plus 2E giving rise to Cd, and this has a E naught of minus 0.403 eV. So you have a reaction which is Cd plus Te giving rise to Cd Te. This is how galvanic process will occur. You will have to keep stirring this solution, and this gives you a deposition rate of 0.01 to 0.1 micron per minute. So it's a cheap process. You can do it in air, and then you will have to anneal these films to achieve. Similarly, you can do MOCVD and other chemical processes, which I am not going to go into details of that. Okay. So, in these thin films, what happens is that you have a microstructure which is something like this. So, you have a I think we have run out of time today. We will do some of these things in the next class, looking at the microstructure, looking at the material improvements that can be made in CDTE, the treatments that are done in CDTE to improve the quality of CDTE as a solar cell. So, we will look at those in the next class. In this class, what we have done is we have learnt about cadmium telluride as a technology, how is it made, and we will do the next whatever remaining parts in the next lecture. Thank you.